This talk is ended.
So, good afternoon, everyone. I am going to give my annual evolution talk on tunable topology via controlling spin chirality of non-collinear antiferromagnet MN3 I have done this project under the guidance of Dr. Ashish Kumar Nandi. And those are the outline of my talk. I will firstly go to the introduction part. I will introduce about nodal line semi-metal, wild semi-metal, and anomalous Hall effect in wild semi-metal. Then I will go to the motivation of my work, that is the topological phase transition in non-collinear antiferromagnet and non-trivial transport. Then I will give a few first principle calculation results. The details of the crystal structure of MN3SN and electron structure details will be given after that. Then I will give a effective model analysis. I will show the symmetry analysis, and I will conclude with result and discussion. Then I will give my future aspects. Those are the outline of my talk. So firstly, as we know that in topological semi-metal, in the Brillouin zone, two conduction band and valence band touches at each other at any point or at a certain region. Depending on the band touching and the symmetry and other things, we can define different types of topological semi-metal, that is direct semi-metal, wide semi-metal, nodal line semi-metal. So here, firstly, I am going to discuss about some brief introduction to the nodal line semi-metal. So the nodal line semi-metal is where the conduction and valence band cross each other along a curve in momentum space rather than at discrete points. So for nodal line semi-metal, the band touching is in a line or in a curve. So depending on this band touching, there can be nodal line, nodal ring, or nodal chain type of semi-metals. And this band touching has not dimension 0. On other case, for Dirac and Weil case, the band touching has dimension 0 because they touches at a single point. But here they are touching in a line or in a curve. So here the band touching point has a dimension 1. Now we can define a integer winding number for this nodal ring semi-metal also, because around this band touching we can define a closed surface. For this closed surface we can calculate the winding number that should be an integer value. So that is the topology which is coming for nodal line semi-metal. Now
Subhadip, slow down. First of all, go slowly when you're running through very quickly. Okay, just a question here.
Yes.
When you are talking, the picture that you have shown, this 3D plot on the left corner,
Yes,
that
yes,
one.
yes.
So there is a nodal line where the two bands are clearly crossing, and the cross section is this circle.
Yes, this circle.
But if I do a small k expansion, let's imagine that my Fermi energy is exactly sitting on that cross section, that disk.
Yes.
Okay, if I do a k dot p Hamiltonian, does it give me a linear behavior?
For the k dot p Hamiltonian around this point, that will give a linear that k dot p Hamiltonian will be in that form, that is let's say m0 minus k square sigma, that will be dk dot sigma type of Hamiltonian. dk dot sigma, dk will be dxk, d0k, dxk, dyk, dzk, and sigma will be.
This is a very simple question he has asked.
It will be linear. It will be linear.
Yeah.
It will be linear, but then since you have drawn this picture, I could have pushed the red band further up, right? It will still cut out a cross section which is a circle.
Yes.
But then the band curvature is going to, from this picture, the band curvature could be anything. What guarantees, unlike a Dirac or a Dirac semi-metal, or while there you know that it's linear because of a special property of the band structure.
Yes.
Here from this, you could take two bands and pass them through each other, you'll always get a cross section which is a circle. What tells me that it's a linear behavior if I do a k dot p around this circle? This is not generally true, right? This is pertinent to certain kinds of bands.
Yes, there needs some symmetry for that thing. You cannot.
You are going to say about those things later? Because
Yes. There are some symmetries. There are some mirror symmetry we need.
Okay, go ahead. Fine, go ahead.
So here this nodal line semi-metal has protected by time reversal or inversal symmetry together when absence of spin orbit coupling, because in the absence of spin orbit coupling there will be spin inversion symmetry, so that will protect the nodal ring will be protected in that case by time reversal and inversion symmetry together. Now if the system has a if the system has a spin orbit coupling, so it will break the spin inversion symmetry. So we need another crystallized symmetry to protect this nodal line to gap out. So this is the symmetry is called the mirror symmetry. So here mirror symmetry part takes part to make this protection, to not this gap to be opened. So and for this nodal line, they protect diamond type of surface states connecting the bulk line nodes. So here you can, if you take this projection on the surface below ozone, you can get a diamond type of surface states for this nodal line same metals. Now, if the protecting symmetry, I already called that the protecting symmetry is time dilation symmetry, inverse symmetry, when there is absence of spin orbit coupling, and the protection symmetry is mirror symmetry when there is a spin orbit coupling. Now, if I break the protecting symmetry, what will be happen? This band touching will be gapped out. So this gapped out. So may they be completely gapped out, or they can become two wild nodes. So how can you say that this gapped out giving a wild node? Here is a nodal link, just protecting symmetry is breaking. Now we are getting a wild node. So this can be directly proved by anomalous Hall effect. You just calculate the anomalous Hall effect as around a wild node. A wild node can be a source of very curvature. So they has a huge amount of anomalous Hall effect. But for nodal link same metal, the anomalous Hall effect is 0. So from directly proving the anomalous Hall effect, you can say that there is a topological tuning from this nodal ring to wild node. So just when there is a symmetry breaking happening, you can go from this nodal ring to wild nodes. Now, when we go to the wild, now we are getting to the wild same metal. In wild same metal, there are two non-degenerate conduction band and valence band. They coincide at a point, at a wild node. So to see this type of wild same metal, you have to either break time inversion symmetry or you have to break inversion symmetry, because you have to get two bands who have
No, it's fine for me.
Yes. Hello. Hello. Yes. You need to break either time inversion symmetry or inversion symmetry, because if there is time inversion symmetry and inversion symmetry, the system has a Kramer degeneracy, so the bands will be degenerate. So to break this band to non-degenerate, you have to break either time inversion symmetry or you have to break either inversion symmetry. So you can see this type of wild symmetry only in time inversion breaking system or inversion breaking system. Now, only for this wild node, to protect this wild node, you need only the lattice translation symmetry. You do not need any other extra symmetries to protect this. And this wild same metal has few interesting topological properties. They are very robust to any perturbation. So let's you give a mass term to here give a perturbation to this wild point. So what will it will do? This perturbation will not gap out this wild same metal, because if you see the low energy Hamiltonian around this wild point, you see that for 3D wild node you get the Hamiltonian sigma x px plus sigma y pi plus sigma z pz. Now if you add a extra mass term, it will be absorbed by some sigma term. So there will be no band opening. So this wild same metal are very robust to any perturbation. They are very stable. So you cannot make this gap out. And this wild same metal can be think as a magnetic monopole in the K space, because if around a wild node you consider a closed surface, you consider a closed sphere. On this sphere you can get a non-zero Chern number. So you around this wild node you can get a non-zero value of Berry flux. So for two different type of wild node, there will be two different type of topological Chern number or topological chiral charge number. So you can say that a wild node in a total Bilwa zone, there are minimum two wild node. One has a topological charge number 1 and another one is -1. So one is called the monopole and another is called the anti-monopole. Now I have this wild same metal Bilwa zone, 3D Bilwa zone. I have two wild node at this position and that position. So between these two wild nodes, this Kx Kz plane can be thought as in this case KZ plane, there will be a Chern number C equal to 1 and all other plane, this plane, there will be no Chern number. So between these two plane, there will be, between these 2 points, there will be many planes that can be called as a Chern insulator, and they have a chiral edge states. So just connecting this chiral edge state between these two wire node in surface below zone, you can get also a Fermi arc type of surface state for wire node. For top surface, you can get this type of Fermi arc. For bottom surface, you can get this type of Fermi arc. So in wire shear metal, they also shows exotic Fermi arc surface states. Now, anomalous Hall effect of wire shear metal. As I told before, that between this, let's say I have a wire node at plus K0 along KZ direction and minus K0 along KZ direction.
Subhadip, your slides are not changing. Is it just for me? I am still stuck with the slide titled wire semi-metals and 2 lines written there. Have you moved
No,
to a
sir,
different
I think it is changing because
Yeah, I can see it.
You can see, so if it is a local problem, it's fine. I'll log out and log
Just
out.
escape and then again.
Yeah, that's okay. I just wanted to check. Please go ahead. Yeah.
So as I told before, if I have 2 wire node along KZ direction at plus K0 and minus K0. So between these 2 wire node, the KX, KY plane, that can be thought as a 2D Chern insulator, because between these 2 wire nodes, this plane has a Chern number 1 and all other plane has Chern number 0. So between these 2 points, the planes are a Chern insulator, and they have a chiral edge made of Hall conductance square by H. So we can say that between these 2 points, there is an anomalous Hall effect for this pair of wire node. That will be just sigma xy square by 2 pi h, and the distance between these 2 wire node, that is 2 k0. Just integrating the total Hall conductance for these all planes, you will get a anomalous Hall effect. That is the anomalous Hall conductivity, which can be written as square by 2 pi h into 2 k0. So for a time reversal breaking wire shear metal, that is for a magnetic wire shear metal, you can get a huge amount of anomalous Hall effect around these wire nodes. So this is a interesting property for wire nodes or wire shear metals. Now for the motivation of my talk, that was the paper which I studied first. It was the paper by Yang and Yang Sun and Yang Zhang. They first studied topological wire shear metal in the chiral antiferrometric material Mn3Sn and Mn3Ge. So that was the first study of a chiral antiferrometric materials wire shear metal properties. So they have for this antiferrometric structure, antiferrometric spin structure for Mn, and for this crystal structure, hexagonal crystal structure, 2-layer hexagonal crystal structure, they have calculated with first principle calculation this Mn3Sn and Mn3Ge band structure, and they have found that for spin orbit coupling, if the system has a spin orbit coupling, so they are finding this type of band structure. They are as their sister compound Mn3Sn and Mn3Ge. So those 2 compounds have the similar band structure, and they see that there is a at J point, at K point, there may be a touching, but that's not a wild node type of touching, because when they zoomed it, they see that at this J point, there is a slight energy gap, and those bands are also doubly degenerate. So that cannot be a wild point. That can be said as a Dirac point or Dirac point. But around K point also, when they see that there is a slight gap, but because in high symmetry points in the path, in the band structure, there should not be a wild point. Wild point should be around the high symmetry point, but not in the high symmetry point. So they also showed that in the Bilua zone, in a particular path, in first Bilua zone at K point, there will be 6 set of wild nodes, and this wild nodes is coming due to some mirror symmetries from here. So for this anti-ferromagnetic 120 degree, for this particular structure, they have started the first principle calculation, and they showed that there may be some number of wild nodes. So that was the first study.
What was the typical moment size of this magnet?
3.2 mu b. That's
okay. Can from there you argue that this is because if it was okay? So if it is your argument is based on a particular classical magnetic structure that you have drawn.
Yes.
Okay. But rarely, I mean, can you argue that it is close to a classical magnet and not a quantum magnet? Because if it were a quantum, what temperature was this thing done?
Temperature.
DFT typically is done at what temperature? When you do density functional theory, what temperature do you do it at?
Mainly at One second. I just trying to
This you should know.
Density constant is what? This is simple.
at 0k, I think at 0k.
You think you are sure, not sure? I mean, you
I
are
am sure.
Zero temperature, these are ground state calculation or
0 temperature, 0k temperature. I just confused with this.
okay. So,
Or those are ground
no,
state.
so the point of asking that question was if the DFT clearly is a zero temperature calculation, you have chosen a magnetic structure.
Yes.
I also asked you a question about the size of the moment.
Yes, 3.2.
Yeah, so there must be a connection to these two questions, right? I'm not asking two unrelated questions. So the question is, if these were, for example, if this moment size was half mu v, would you be able to trust your calculations of this magnetic order?
Half mu b with the moment size.
You know what is being asked? Question being asked is how classical is your ground state? This is an actual material, I suppose.
Yes. Real material. Yes.
Real material. So if the moment size is small, but
Yes.
the moment size is large, what tells you? Are you in the classical regime or quasi-classical regime or quantum regime? If you don't know, you should think about this question.
think about spin fluctuations.
Yeah, so what controls, if you do a Holstein-Primakov transformation, think of spin wave excitation.
Yes.
What is the correction to the classical ground state? What does it go as?
Classical ground state. Just SI crosses.
It goes in inverse of the spin length. That's why I was asking. The spin length is large. You can treat it crudely as classical. Crudely.
Because here the longitudinal fluctuation it cannot capture. So that is that. So also
Yeah, so it's close to a classical ground state. That's why.
Yes.
This mirror symmetry all depends on a particular magnetic orientation.
Yes.
If it keeps on fluctuating with large quantum fluctuations, I'm not sure how this kind of studies be done anyway. Okay, so that's the thing you should consider.
So the DFT will be valid there because you are calculating the zero temperature.
Yeah.
Yes.
Even if it's a small spin-off system, also it will work there. Okay, but that may not be so. This the lifetime of this while node, which will be zero temperature, that will not be true if I increase the temperature.
Yeah, and even at zero temperature, if there are large quantum fluctuations, then if your moments are typically large,
quantum
yeah. Okay, go ahead.
Subhadip, probably I have missed. So around K point, you said that your band is actually gap.
Yes, there is a teeny gap around this K point.
So why there are wild points?
No, it is calculated in a particular direction in this gamma k m direction. If you calculate in other direction, you will get a certain direction. You will get six pair of wild node. It is calculated in just a certain direction. In Bilwa zone, there will be 6 K points. So in a particular K point, around 2 K point, you will get these nodes, wild nodes.
Oh, but that is not apparent from this figure.
No, not apparent from this figure.
Yeah, because these are high symmetry points and wild node doesn't appear.
No, wild node does not appear in the high symmetry points.
Something you are missing also some point. That if you look at this K point around this K point, so this twofold degeneracy they are pointing to say that this can give you a wild point. Okay, but whereas in a J point it's a fourfold degenerate, so it will be a Dirac point. So one can look for the wild point around K point.
Yes.
That is the main message from here. Okay. Yes. So then one can look more on these details. So that he will come in a minute.
Yes.
Okay.
Okay, sir.
Yeah, around Z point also that is absolutely not wild.
Yes, there is 4/4 degeneration. So that's a Dirac point.
So that's why they are not looking around the Z point.
Yes. They are looking around the K point because for their twofold degeneration is there.
Yeah, go ahead. Yeah.
So I am going to the next motivation of my talk. Here I am showing that these people, this Hansen, Tesai, Tumo, Higo, this group, they have studied the electrical manipulation of a topological antiferromagnet. So,
Subhadip, one point.
Yes.
That when you say that this Hansen, Tesai, that group, this is not the group, this is the student.
Okay.
You just know this thing, that you cannot say that this is his group.
Okay.
Until and unless you know the textual group, that is by this author, you can say that author.
Okay. Okay.
Group will be maybe Otani and Nakarsuda. Who's it?
Okay. Okay. So they have studied that if there is an electrical manipulation, then there is electrical manipulation, then these spins, these antimagnetic spins, they can feel a spin orbit torque, so they will be rotated. So the magnetization direction can also be rotated by an electrical manipulation. So when the magnetization direction is rotating, they have calculated, that's the experimental paper, they have calculated the things in M3SN, they have calculated the anomalous Hall effect, and they see that there is a switching in the anomalous Hall effect, and they also see that in the Bilwa zone, where in the K point there is a 2I node, this nodal direction also changing with the change of the magnetization. So by applying an electric field or electric manipulation from outside, you can also change the wire nodal direction. So they say that if for this octapole, magnetic octapole, there is two layers manganese atoms. So there is a direction of this octapole polarization. So if we change this phi, if phi is pi by 6, then this wire node direction, that is from plus to minus, this direction is in that way. But if phi is changing, let's say phi is pi by 2 or pi by 6, this wire node direction also changing. So by an electrical manipulation from outside, there is a topological nodal direction also can be changed. That is a very interesting thing to study in topological antiferromagnets. So this is the good. This is a very good work, and there are also many work also chiral spin notation of non-covalent antiferromagnet by spin.
Just remind me what was phi in this calculation?
They have firstly calculated the anomalous Hall effect, and
I'm asking what is phi? What is small phi?
Phi is just the angle of this. Phi is the polarization rotation angle. This magnetization rotation angle.
No, this is the octapole. That octapole orientation is written there.
There is a picture there, right? There is a octapole moment rotation.
Octapole moment rotation.
Yes, with magnetic, with electric manipulation.
No, where is the electric? That is the rotation, but how is the electric field varying? I mean, that is the rotation of the moment with response to the electric field, but how is the field being? It's a cyclic field, I presume. I don't know.
No, from outside, when you put a electric field, then there
what nature? What is the form? Electric field is not a word, right? There will be a functional form. It's an analytic calculation. So I presume they must have used some kind of
No, sir, they did not analytically calculate. They just calculated, that's experimental observations. After that,
no, but the electric field was still applied, even if it is an experiment. Okay, if it is an experiment, they must have applied the field, right?
Yes.
The field is not, I presume, a random field.
Yes.
There must be some control. Is it a sinusoidal field? So there has to be, I mean, you're showing some phi variation across these 6 plots, which is the rotation of the moment direction. All I'm asking, what is the systematics of the sort of, the stimulus? This is the response.
Yes.
What is the field?
I do not know exactly what is the...
No, you should know this. I mean, if you're showing a variation, it will be a question of, is it a faithful variation? Does it rotate it twice? Okay, I mean, if the field cycles twice, does it rotate by, let's say, comes back to itself? There are so many questions one could ask you.
Yes. Okay. So actually, he doesn't. Maybe I can tell this thing. So what happens is that they put an electric field. Actually, that is perpendicular to the magnetization direction.
Okay.
So in that way, they create generate another magnetic polarization, which is perpendicular to the current direction as well as the magnetization.
Yeah, and then I presume you vary the electric field in some way, right? A static electric.
Yeah, so then you can rotate the electric field there. So that means that the rotation, even if you don't rotate it, that magnetization what is generating there, the spin polarization,
Will give you a fixed angle.
Yeah, so that's
some phi.
Yes, phi. So some spin torque will be there. That's
Yes.
why because of spin torque, the real spin will rotate.
Okay.
So once you rotate that actually gives you a rotation of the octapole movement.
That gives you a new equilibrium direction for the octapole movement.
Yeah, so you can rotate the spin. That is the coherent rotation of your all the spin.
Okay, I see. Okay.
So actually, that means E dot B term is a chiral anomaly term. They introduced. Yeah?
Sorry, E dot B.
Yeah, because E is perpendicular to B. You are saying.
So no, electric field is B. You mean the magnetization direction?
Magnetization direction. Electric field is perpendicular.
Then there is another magnetic field which will be basically the induced magnetization that will create it there because of the Edelstein effect.
Yes.
Okay, so that actually this induced magnetization gives you a torque. It's basically the antichromatic manipulation and it's the same funda of this antichromatic switching.
But the material is topological insulator, is it?
No, sir. Real is a MN3SN. That's not topology.
Why?
If you look at the picture, yeah. Why?
So then, if, like the B or the magnetization that I am talking that you are talking about, and the electric field. So if it is coupled to the intrinsic magnetization and the electric field is coupled, so they will generate some anomaly term, kind of anomaly term.
Orijit, I think what he perhaps is trying to mean is the rotation of the local moments, right? There is another story, another effect that probably what Orijit is trying to point out what happens to the electron. It's still a semi-metal, right? So the electrons will pick up some Berry phases, non-trivial phase, some anomaly terms. But this is more so with the manipulation of the fixed local moments. Is that a fair statement to make?
Yeah, it's a manipulation of the local moment, actually, of course.
No, but I think Arijit is asking a different question. He is probably asking what happens to the transport in the problem in presence of this field.
That's what.
At it. This chiral anomaly dot beta, where your current is not conserved, maybe they are not looking at it.
But it will still be there. There is some effect of what Arijit is
because
saying.
Because in any material, while you will have this, if you apply E dot beta, E and beta, then you will have a chiral anomaly related current, right?
Yes.
But the main point you have to look through some transport or some magnetoresistance, which gives signature of this.
Sorry, sir, but Hall is already measured in this sample, na? Anomalous Hall.
No, measurement is fine. The question is, see, I mean, as I understand, the motivation of this experiment is perhaps to rotate the core spins, the magnetic texture. Now, what Arijit is trying to point out, by the way they are doing it, that also induces another effect. Okay, so the question is, is this another effect going to screw up what the motivation was? That yes, you changed your core spins, but in the process you induce something else also in the transport.
So,
does that change the physics of the problem? That is the question.
In this way, you can think about that. If you want to screw up this thing, then you have to change the band structure dramatically. But in this case, they want to rotate this spin, then the band structure remains the same. Only the wild point that the band touching will change the position.
Yeah. But the question still remains, right? I mean, I don't know the answer. I mean, maybe
that one has to look at it in a theoretical way. That whether
so how is it? Is it a big effect or a small effect? It depends also, I guess, on the numbers. How strong is the field that you?
So these numbers, this anomalous Hall effect, whatever measurement is there, then in that measurement you cannot capture even if it's there.
Yeah,
Okay.
I guess that will be captured through other, because you may have some anomaly related phenomena.
But you need something else to measure it.
Yeah.
You cannot measure with this anomalous measurement.
You have to look at the magnetoresistance to see if there are negative magnetoresistance coming on. And those are different story, I guess.
So here only thing is that the polarity or the orientation of your wild movement, they are changing. That's why you have a switching of this anomalous Hall effect. That's what one can say. Otherwise, I think other effect it will need more deep study. Okay, go ahead.
Okay, sir. Now I will talk about non-collinear antiferromagnet. For antiferromagnet triangular spin structure like this, with the ground state is characterized by a stagger chirality. This stagger chirality is the sense of rotation of a spin about a triangle, which can be defined by this formula k equal 2/3 s1 cos s2 plus s2 cos s3 plus s3 cos s1 dot ez cap. Now for 120 degree order, there are only two chiralities, plus and minus, which are coming from the sign of the chirality kappa. So let's say I have this structure, I have this S1, S2, S3, this spin. If you go from S1 to S2, this S1 cos S2 is the vector chirality, but the stagger chirality is, if this S1 cos S2 will give you a plus sign, this S2 cos S3 will give you a plus sign, then S3 cos S1 will give you a plus sign. So we will get a overall plus sign. So you can say that the stagger chirality for this structure is positive, and for this other structure, you can see that from S1 to S2, when you go, there will be S1 cos S2 will be negative, and this total thing will come as a negative thing. So stagger chirality for this structure will be a negative. So we are defining this type of two triangular structure where for one case there is a stagger chirality positive, and other case is negative. This structure we are calling as anti-clockwise, and this is we are calling as clockwise. And I am going to see for a material M3SN these two type of magnetic structure. What is the band structure? What is the topology on these two different magnetic structure? What is the topology? And to see this thing, firstly, as I am going to discuss about the ab initio calculation result of MN3SN. So here I am going to discuss about MN3SN magnetic structure. In MN3SN, those rate are Mn atom magnetic moment, and Sn is the middle one. These Mn are in a 120 degree non-collinear antiferromagnetic triangular spin structure. And as I talked before, we are going to see these two type of magnetic structure. One is anti-clockwise and another is clockwise. These two type of magnetic structure, we will see the we will do the ab initio calculations for these two magnetic structure. So for MN3SN, these two magnetic structure, what is the change in topology, we will see. So to see this, we first calculate the first principle of electric structure calculation, and the electric structure calculation was done within the framework of density function theory implemented in the Vienna ab initio simulation package, and the exchange and correlation energy were treated under the GGA approximation, that is general gradient approximation, following by the PV parameterization scheme. Then the cutoff energy during calculation is fixed at 500 electron volt, and to sample the Bilwa zone, a gamma center KMS has taken during the self-constitutive calculation. We have done the calculation with spin-orbit coupling and without spin-orbit coupling. We have done the organization procedure using file package, but now I am not going to show those results. I will only show the vast calculation results here. So for first principle calculation, we have to idea about the structure of the primitive shell structure of MN3SN. It is the primitive shell structure of MN3SN. Those are Mn atoms, and this is the Sn atoms. These Mn atoms are a triangular-like triangular layer. Here there are two layers of there are two layer hexagonal structure, and for this structure, the value of the value that we have taken from the experimental value of the lattice parameter, those are A equal 5.65 angstrom, B is 5.65 angstrom, and C is 4.52 angstrom, and we have taken alpha, beta 90 degree and gamma 120 degree. And each Mn atom has a magnetic moment 3.2 mu b, as I told before, and the magnetic ground state is a non-collinear antiferromagnetic state. Now this is the below. For this structure there is a 3D Bilwa zone. We have just taken a 2D cut of this Bilwa zone. So this is a first Bilwa zone. That's a gamma point, and that's M point, and the H point are called K point, and these B1 and B2 are the reciprocal vectors. And now, for as I told before, for these two magnetic structure and for this particular structure, we have calculated the first principle electric structure details. So when we calculate the band structure without spin orbit coupling, so we see that for two different standard chirality, for anti-clockwise and clockwise, you can see that for these two cases, we have plotted the E minus EF, we put EF at 0. So we have plotted the band structure along the path gamma, MK, gamma, AL, this path, in this path. So for these two standard chirality magnetic structure, we are getting same type of band structure for without spin orbit coupling. When there is no spin orbit coupling, these two band structure are equal. There are no difference between these two band structure. So when there is a no spin orbit coupling, the band structure has no discrepancy. But if we apply a spin orbit coupling to the system, then we calculate the band structure. Then we saw that for standard chirality anti-clockwise, there is a along K point, there is a nodal ring type of band touching for this standard chirality anti-clockwise. But for clockwise, we can see that this nodal ring of band touching is now opening, gapping out. So there is only wild nodes. So there is, for these two different structures, for anti-clockwise, clockwise, when we are taking spin orbit coupling, we are, for one case, we are getting a nodal ring around this K point, and for another case, for clockwise case, we are getting a wild node around this K point. So there is a topological difference between anti-clockwise magnetic structure and clockwise magnetic structure when we are applying a spin orbit coupling to the system. So that is so we can say that there is something is happening when we are just changing the staggered chirality. There is a topological tuning between a nodal node to a wild node. So that is the observation from our first initial calculations. And we have also calculated the energy. Here in the x-axis, those are the angle. Let's say I have this downstate at this clockwise structure. So this is the theta angle. I have rotated this spin in 60 degree. For this moment, I rotate in the right side, and for this, I rotate in the left side. So we get this structure. For that structure, when we are from first calculation, when we are calculating the E minus E clockwise, we see that there is a big energy. So that is not a stable structure. But when we are getting for this structure, the energy difference between this structure, for that structure and that structure, is very small. That is in the order of 1.4 millielectron per manganese atom. So the energy difference as between these two structures is very small. So we can conclude that there can be spin orbit staggered torque, which is doing the job to transition from this structure to that structure. We can go from this structure to that structure with a staggered spin orbit staggered torque. So this is the result from first initial calculation.
So Subhadip, just go back to this. So this, I presume, is the energy calculated directly from the DFT, right?
Yes.
Have you estimated you could estimate the J if you wanted to write a spin model.
Yes.
Have you guys looked at the J?
Not yet. So far, I do not see that.
We can look at it.
Yeah, because so I think the interesting point is, because there is this big barrier in between, if it is a spin-only model, just an effective model, one could see if there is a way around it. Are there zero modes that take you from this texture to the other texture, avoiding this large energy cost? That is a cost at a classical level. If one sees that, then one can see if there are quantum fluctuations. It's an interesting property. But the J1, J2 model would be good to look at, and then do a Holstein perhaps.
So we want to, so in this kind of chiral structure, we have a plan to do this magnon. Okay. So
yeah, I think it's important. I think you should be able to get some weird zero modes that can come out. I don't know, Ravi, maybe not in the audience.
We have to, once we get this J's and D's, because there will be a lot of D's, G, J, all will be there. Yeah. Even not only that, we can have a higher order spin interaction in churn people doing that.
Yeah, so it's true that it might not just be a J1, J2 model. It might have to go higher.
So all the J's we will calculate and D's.
Yeah.
And then maybe we can talk to Ravi to
because this is probably Ravi's, he would know these things much better.
Yeah, so we have a plan, then let's see that.
Okay, sure.
Okay. So those are the discussion for my first initial calculation. It is shown that for associative in case.
Go back to this one. I think he's not that clear to the examiner. So I want to just clarify to Arjita and others, these things. And Anamita. So these 2 points, basically this clockwise, whatever the staggered this thing that numbers, that chi +1 - 1. So people all talk about this coherent rotation of the spin. So if you rotate all the spin in the same direction, then actually this number, the chi, will not change. Okay. So that means the chi will not change. So what actually happens that in this real system, that only the while points rotate around the k point. So that's what the earlier experimental paper, nature paper, they did it. But more things it will come here that with the spin rotation, whether there is a topological transition. So since there is a spin orbit torque can do the job to rotate those spins, then I can actually change from 1 to spin, to keep the third spin fixed. If you look at the left and right picture, third spin fixed, 1 to spin I can rotate in a different way. For example, 1 spin I can rotate clockwise and 2 spin I can rotate anti-clockwise. Then actually one can go from this staggered +1 to staggered -1. So in that way one can, we see that there is a topological transition.
But Ashish, I mean, just maybe we can discuss this later. But just to ask, so when you mean coherent rotation, that's a rotation of all the spins with a fixed relative. Yes or no?
So you mean the coherent rotation? All spins I am rotating by same angle.
Yeah. So the transformation that sort of rotates your while points is which rotates?
Coherent rotation.
It's a continuous rotation of all the spins simultaneously.
Yeah.
And you are suggesting that you are going to sort of
staggered rotation. I want to put
staggered rotation. But will it have an implication on the while points itself? And should it?
That's what the point. Then that's what he is going to show.
Okay, he's going to show. Fine.
Yeah. So this is the actual main message from this picture.
Yes.
And I don't have to he has to practice a lot, and he's just screwing up all the new physics there.
Because from the previous plot, what I understand is that by changing the staggered S1 dot S2 plus S3, so one case clockwise case you are getting the nodal semi-metal, and the other case while.
Yes.
Another is going while.
Another is So around k point here it is. So in the first plot, around k point should I put it while, because the nodal ring is the other point. Or
the left one is the nodal one.
This one is nodal one.
Yeah. So while is also there, right? Here.
No, while is not there. While is the right one.
Here,
So around k, this crossing, how should I understand? Or there is no crossing?
Now you have to, so only this is a 2D picture, no? So it is only one direction picture. You have to, so that he has not done it, but I have done it, something that this, you will find there. Okay, so once you rotate all the direction around k point, so for example, it is mk gamma, okay, that is the line. Now you rotate that line with respect to k. Then actually, if there is a while point, then once you rotate by 1 degree, then bands will gap up, right? But once if it's a while node, then band will not gap up. So it will form a ring.
Yeah, it is form a ring, and now you are really getting a while.
Yeah, now you are getting really a while.
So your previous problem was system was protected by mirror symmetry. So I would say it was kind of mirrored.
Time reversal mirrored. There are some.
Time reversal is there in the first case.
I will show the symmetries.
So those symmetries he is pointing out that what will be the low energy Hamiltonian that he is going to show.
Okay. The second is the charm insulator. So, sorry, time symmetry broken.
Yes.
Yeah. So time reversal symmetry is broken everywhere because it's a magnetic system.
Yeah. So
it's a kind of Muller symmetry into time reversal symmetry.
Time reversal symmetry is broken. That I understand.
Yes, time reversal symmetry.
Time reversal symmetry is always broken there, but
that is broken by the Mn atoms.
Yeah, it is broken by the magnetization of the Mn atom.
No, but Ashish, this we have discussed earlier that for a conventional antiferromagnet, we can recover time reversal by flipping and doing one translation. They will get back to itself.
So that is actually, I agree. This is basically a talk about gliding kind of symmetry.
Yeah, so I don't know. I mean, this texture looks quite complicated. So I immediately it's not apparent to, but that if I flip all the spins and then, of course, these are these are not half spins. So time reversal operator has to be appropriately used.
Yeah.
So I don't, I mean, I'm sure people would have, I don't know this. I mean, people would have looked at, in this case, is time reversal broken?
So I'd rather say that this seems magnetic system, and also I have not looked at this antiferromagnetic. So inversion symmetry is there, but time inversion symmetry is broken.
I mean, time reversal might be a weird thing here because
So that's what I was asking. Whether MN atoms break time reversal, because when you get wild points, then either inversion or time reversal, one of them has to be broken.
Yeah. So
you are saying with spin orbit coupling.
Sir,
so
I think I
inversion
can.
here only time reversal symmetry is broken. Inversion symmetry is intact there.
Sir, I can comment.
But with spin orbit coupling.
So what do you want to say?
For here, when there is no spin orbit coupling, so for a nodal ring, you need time reversal and inversion symmetry there. But here with SOC, in that case, there are two cases. There is time reversal has broken for SOC. So,
how are you saying that?
How do you say?
See, a Hamiltonian. See, there is a principle. A Hamiltonian having a magnetic term does not say anything about whether the symmetry is protected or broken in the ground state. There are two different things. Okay. So you can do your analysis of time reversal in the Hamiltonian. Think of a Ising model. Ising model or a Heisenberg model is a rotation symmetric model where the ground state spontaneously breaks your rotation symmetry. Okay, so in that spirit, one has to be a bit careful, particularly if you have just a line of up down antiferromagnet. You can flip time. Let's say half spin. You can flip time, so that will go up, will go to down, down will go to up.
yes.
But then you can take the entire lattice and shift it by one lattice spacing.
Then it will remain the same.
Then it becomes time reversal symmetry. In an finite system, everything gets broken. Infinite or periodic system, this will recover your time reversal symmetry. So the question here, your spin texture in the ground state is quite complicated. So what Arijit was trying to point out, when you are saying time reversal symmetry is broken and inversion symmetry is preserved,
Yes.
how do you sort of justify that?
Yeah. You have spin orbit coupling also. And why spin your inversion symmetry is there?
So one thing is that here I say that so if I have a touching, then both are there, then the touching will be there. But if time inversion symmetry is broken, then I will get two wild points.
Yes, minimal 2. Yes.
Minimal 2 wild points. And this is the case. So minimal 2 wild points we are getting here.
Yeah, I mean, it's from the answer to the question kind of way we are going, but it will be good to discuss this.
Okay. We can discuss it later. Yeah, because the symmetry thing is not clear to me why it is getting broken.
Yeah, I mean, it may be.
Let's go to the symmetry part, then maybe it will be clear. Okay.
So those are the thing we got from the ab initio calculation. For SOC driven case, we are for anti-clockwise structure we are getting a nodal ring, and for clockwise structure we are getting two wild nodes. And we have also seen the energy difference between the clockwise and anti-clockwise, and that is very small, the energy difference. So we can say that this transition can occur via a spin orbit staggered torque. Now, define symmetry operation in these spin structures or these magnetic structures. Let's say for two different magnetic structures, the two layers are related by certain mirror symmetries and certain combination of mirror symmetry and time reversal symmetry. Let's effect of time reversal and mirror plane on spin direction. Here, we have a moment. We have then the effect of the time reversal symmetry that will flip the moment just. So that is the effect of time reversal symmetry. But what is the effect on mirror plane? Let's say we have a mirror plane. So if a moment is perpendicular to the mirror plane, the direction of the movement will not flip. But if it is parallel to the mirror plane, it will be flip. That is the basic thing under a time reversal and mirror plane, how the moment transfers. And for our structure, we have two structures, for anti-clockwise and for clockwise. This is the for anti-clockwise structure. And let's take these two spins, just this spin and this spin, and let's say there is a MY mirror operator. So what will be that case? That spin will be in that direction, in the below direction. So there need another symmetry, that is T symmetry, which will be there MYT, which is getting this to that point. So there is a MYT symmetry in this structure, and along H direction, if for this spin, you can say that this mirror symmetry MS, mirror operator MS, it is taking this spin to that direction. So we can say that for this anti-clockwise structure, there is a MYT symmetry and there is a MX symmetry. There is also C3Z rotation symmetry because this is a 120-degree structure. So what will be the value of how can we define this mirror symmetry in the terms of Pauli matrices? So we can say that from this structure to that structure, to go this spin moment, you can take the matrix MYT as a third component of the Pauli matrix, that is minus sigma z, minus of third component of Pauli matrix is the minus sigma z, and MX you can take as minus sigma z also, and there is a C3Z, that is identity matrix. And for clockwise, similarly, for if you take these two spin, just only these two spin, you can see that for MY mirror operator, this is just there has a MY symmetry. Just this moment is transforming to that moment. So there is a MY symmetry, and along H direction, this moment will be on that direction for MX operation. So we need another time reversal symmetry MXT, who will back this spin to the and that direction. So there is MXT, MY symmetry, and C3Z symmetry. So those are the two symmetries. And here you can also say that for these two spin, this if you see the so operator, this operator can also be write as a Pauli matrix, that is sigma z. So here the MXT is sigma z, MY is sigma z, and C3Z. And those are the all symmetry for these two type of spin structure. For anti-clockwise, there is MYT, MX, and C3Z, and for clockwise, there is a MXT and C3Z and MY.
So, Arijit, I think these are all the symmetries one can find. So even this parallel structure. So what Anamita was saying, that that the structure remains the same under this kind of symmetry operations. So.
Yeah, but what is the? I mean,
the question was different. I guess the question was.
Yeah.
I have the, let's say, I know that from band structure, what are the symmetry I break, right? Like time universal symmetry, I get to see that there are wild points. Now, look at the ground state, and ground state is anti-ferromagnet. Looking at the ground state, is it going with the same as like what symmetry is then broken? If I ground state seems preserving, anti-ferromagnet, preserving time universal symmetry, but looking at the Hamiltonian, and then I'm saying that wild points is band structure, I'm getting wild point because of the symmetry breaking or time universal symmetry breaking. But looking at the ground state, same symmetry is there, right? Your question was like this.
Yeah, but Kush, I mean, this probably is a general question. When you define time reversal symmetry, let's say if you are talking of a half spin system, yes, the operator that we look at is charge conjugation times e to the power I sigma y. Right. And that actually, I mean, we just transform the Hamiltonian to see whether there is time reversal symmetry or not. But Ashish, what is this? I mean, if I am to write a spin time reversal operator for here, I need to know what is the spin. So the moment is clearly not half. He said some number 3 point something. In terms of mu b, I mean, what is the closest S magnitude one can think of for the moments?
Here is 3.2.
Yeah, I mean, this perhaps one has to go back and look at. So converting it into what, S equal to 1 or S equal to some in mu b, some number in mu b. That number one has to construct the proper time reversal operator. Kush, off the top of my hand, I don't know. So we use a larger representation of sigma y for.
Yeah, that's the. I'm also trying to understand that what is the meaning of, let's say I have this ground state where I'm showing some.
Yeah.
And the spin is showing some antiferromagnetic order.
Yeah.
And then it seems that symmetry is preserved, right? I mean,
the answer says that the symmetry has to be preserved.
Yeah, according to that.
Yeah, now, but then
the ground state, if I look at the Hamiltonian and if I define some operator like time universal operator, inversion operator, now from that I am going they are getting that there is a symmetry is broken sometime, and you get to a spectrum. That
Yes.
is the spectrum. Now,
Yes.
actually, is it there is a connection between this structure and the spectrum we get?
Well, there has to be, right? I mean,
now what that this spin represents now? Is it a real spin they are trying to say, or the Hamiltonian I am trying to write? They are trying to write in what language? Like it's
so I think this is Ashish. This is more like a this Heisenberg type model you are trying to construct, isn't it? When you draw these spins, the red arrows and the
these are all real spins. So this
Yeah.
symmetry, it is symmetry. These are drawn with respect to the
Real
magnetic configuration, real spin magnetic configuration in the real space.
So the question, Ashish, then is, I mean, if this is not S half, I mean, it's clearly greater than spin half, the spins that you have, because we are almost looking at a classical ground state, so the spin length has to be large. So one has to slightly construct the time reversal operator looking at the spin length to show that indeed there is time reversal that is preserved. That is one sort of thing one has to look at, I guess.
No, in this case, that what people say that what are the literature other people have done is that time reversal symmetry, they took it like the spin flipping only. So they have not considered the time reversal symmetry for the S half or S equal to half or S equal to 2 or S equal to 1. Only they say that how does under the time reversal symmetry how my spins are behaving. That those are real spins are behaving. So they only consider by time reversal symmetry.
Yeah, I mean that's more of a rule of thumb. But I mean, if one were to look at the Hamiltonian and ask if it is time reversal symmetric or not, then one has to construct the operator.
Yes, that is true.
So this operator, that's why this is the thing, that which operator that two can this
So normally for spin half it will be charge conjugation. It will be complex conjugation times e to the power I sigma y. But for a larger spin, what is the operator? Is it a larger, higher dimensional representation of the Pauli matrices that is exponentiated? I am not sure. Again, perhaps Ravi is a person who will know this off the cuff, or if his student is here, he will know. If somebody is here.
Hello.
Chaprit.
So, but this time reversal, isn't it like connected to the octopole moment of this sample?
No. Here,
No.
it's not octopole moment is here. So octopole moment is actually generated because of your spin orientation.
Yes, but like if I reverse all the spins, the total of net octopole moment changes its sign. So that will break my reversal symmetry, time reversal.
No, the question is rotating the spins equivalent to time reversal symmetry at the level of the transformation you do on the Hamiltonian? That is what we are asking. It may very well be that at the end of the day, it becomes very simple and it simply means rotating the spins.
Yes, Trumpet is pointing something. I guess that this time reversal symmetry are where they are showing some spin, and we are talking about, let's say we have anti-paramagnetic order, then we should preserve time reversal symmetry. I guess there is some connection, like these spins are maybe not the real spin we are talking about, the time reversal symmetry. They are coming from some moments.
No, but under vector addition, I mean, so long as we are doing a vector addition, I mean, if the microscopic degrees or the spins satisfy the time reversal, the octopole moment should also, right? It cannot break.
No. Octopole moment, that satisfaction is coming due from the spins only.
So can you break that connection?
But the thing is, because if I just change the direction of the, means it has been calculated and shown that if I change the direction of all the spins, the net octopole moment changes its sign.
No, that may very well be. I mean, that is okay.
So the net octopole moment, I'm saying, means like here it's anti-paramagnetic.
Yeah. No, but that is true. The question is, where did it come from? So the fact that your octopole moment changes, that the calculation that you're talking about must have done some transformation. Right? We were asking what the transformation is. So you have to do transformation on the spins. The spin texture will give you a rotated octopole moment, and from there you conclude whatever you are concluding. But what is the transformation? If there is a half spins, we know what the transformation is. If these are larger spins, what is that transformation that you do? That is what we are asking.
So in larger spin, people take the.
Hello.
Okay, so this one. And then in order to keep that that whole, basically here the magnetic configuration, that in the unit cell whatever the magnetic configuration is there, the under what transformation it remains the same.
So this
Yeah.
is a global.
People try to find out.
So I guess you have to try to think about is a global time reversal symmetry, a local time reversal symmetry. All this includes, I guess, here.
Yeah. That is Kush is right. That is all the this thing in be. So this is the thing that where the global time reversal symmetry one has to take care. So that
that will come from the Hamiltonian level.
Yes, that's
yeah. So
right.
they are
so that's-
the Hamiltonian in that way. So once I know this all that this symmetry operation for the full magnetic system, then accordingly I have to construct the Hamiltonian.
Yes.
So you are looking as if in a placket here.
Yes.
So I think that's a good point. That if you trying to write down a low energy effective Hamiltonian, then what symmetries are we? I mean, you have to make sure that we are not breaking any symmetry by writing a J1, J2, J3 model. So there might be connections between the spins or certain terms in your Hamiltonian which preserve certain symmetries of the original microscopic Hamiltonian. So I think that one has to keep in mind before one can while deriving this effective low energy Hamiltonian. I think that point is an important point. Yes.
The effective low energy Hamiltonian, if it's a spin one, then it will be different, and if it's a electron,
Yeah, exactly.
Electron
Yeah.
one is to be different.
No, even with spin, I think larger spin, and if the spin is large than half spin, then see, we are at the end trying to go to a classical like model, right? But that should be thought of as, in my understanding, some large n component spin.
And for the classical spins, it will be just like an angular momentum. It changes.
Yeah,
size
see, that
at
is
time
the.
level.
Are there quantums? This I think Kush has added. Are there anomalies in terms of classical models that break quantum symmetries? Normally, it's the opposite way, right?
Yeah, classical symmetry should be in quantum symmetry.
But the other way is not always guaranteed. Which are your anomalies in quantum field theory?
So
Anyway, so I think this we should discuss maybe separately. I think there are a lot of people.
also, I have to just make one point. This magnetic moment, whatever is there, that's what he showed this one. These are actually, you can look at it as a axial vector. That's all. So if you have a spin half, I don't think that you can consider that way.
Yeah, you can't. I mean, because there will be quantum fluctuations, and then that model is.
In that way, actually, this symmetry operations are valid. Once I took this moment as the axial vector, then I can think about this kind of symmetry operation.
Yeah, but the point is, you see, I mean, this notion of putting a vector is bit like saying I'm writing the full quantum model and doing a 1/s scaling, and then in the limit of s going to large values, I go to the classical limit.
Exactly.
That is
Question-
the symmetry of that classical model.
Yeah, the question is, but in terms of the quantum model, there are interaction between various spins. Let's assume you have written all the terms and then taken the classical limit. Then, depending on the question is, the original quantum symmetries, are they broken by taking this limit? By going to the so that is a thing one has to just be careful about. I'm not saying that is
not there actually. This is this
Yeah,
kind
yeah.
of
So this original quantum model Hamiltonian symmetry can be.
So if you do Holstein-Primakov take s going to 0,
Yes,
but on a full term, so all the terms that you can write, then that taking the limit might itself break
kill
some
some
symmetries.
yes, kill some symmetry.
So that might be
Original
spurious.
Hamiltonian.
That one has to be careful of it. That's all.
yeah. That means.
Yeah.
Yeah, but
Okay, so we can discuss this separately because this is a complicated topic. We cannot.
Because the while or nodal symmetrical thing is actually symmetry of the original Hamiltonian that we start with.
Yeah.
Yes.
So going to a classical problem, it's an interesting question, but we have to discuss, I guess.
No, if you have to go this magnetic one, then one has to first get all the J's and then we can ask this kind of question first.
Yes.
But in this case, I think if you show you only the electronic model, two-band model,
Yes.
I don't think it is not that important. Okay, yeah, so we'll go ahead.
So we have right.
Subhadip, can you go back? I have just one. So for the left figure,
Yes.
so if I rotate the structure that you have shown by 90 degree, so will it not give me the same type of symmetries as the right one?
What is the question?
So if I rotate this anticlockwise structure full is there, so if let's say I rotate the full lattice by 90 degree.
Full lattice by 90 degree.
And then will not be the symmetry operators look same then?
Well, okay, yeah. Subhadip answered this thing.
For rotating the whole thing, when you rotate the whole thing, the moment's position will be changed.
No, ultimately if I rotate by 90 degree, so the ultimate one moment location will be replaced by other one.
No.
It will not be replaced by another one, but it will be rotated.
If you rotate by 90 degree, you cannot get this structure from there just by rotating 90 degree.
I'm not getting that structure. I'm saying after rotating 90 degree, your symmetries will be same.
No. That will be not there. The symmetry will be changed now.
C3 will not be there.
Yes.
So 120 degree rotation will give the same thing. C3
No, sir. I'm not rotating the spins. I'm asking about rotating the full lattice. Let's say the left figure I rotate. Just rotate the figure.
The C3Z symmetry is the full rotation of your lattice.
If you rotate by just the figure, just these two layer by 90 degree, this one, then that will be there. Then there will be same structure, but there is no C3Z symmetry will be there. But other symmetry will be there for that structure.
Okay.
No, so C3Z 90 degree rotation will not give the same crystal structure. That is the question.
No, but the crystal structure stays same. Now you have just rotated the lattice.
No, crystal structure. Why crystal structure will remain the
No, you
same?
have to have the rotation. You have to act as the crystal discrete symmetry group, right? You have to respect that symmetry group. Arbitrary rotation will not give you back the crystal.
It's not about the whole system rotation. It is about the crystal, whatever the unit cell you are talking about, that rotation. So this you will see the triangle. If you rotate the triangle by 120 degrees, this triangle remains the similar triangle. So that symmetry you have to preserve. Okay. Go ahead.
So we have written a K.P model Hamiltonian for this structure, keeping in mind these symmetries. So for these symmetries, we have written a effective two-band K.P Hamiltonian. So this Hamiltonian will give us a nodal ring type of dispersion. So there has the symmetry C3Z, MX and MYT. As I already told that for this type of structure, those MX and MYT symmetry can be written minus sigma Z. So I will show that this symmetry is also preserved in this Hamiltonian. So for that we already know that for MX, Miller symmetry around X, this Kx will be minus Kx. So they will be this Hamiltonian H Kx Ky Kz and H minus Kx Ky Kz. They will be related with a similarity transformation. So MX H Kx Ky Kz, MX inverse will be H minus Kx Ky Kz, and MYT H Kx Ky Kz, MYT inverse will be H minus Kx, because T will make Ky to Kx to minus Kx, Ky to minus Ky, Kz to minus Kz, and My will make minus Ky to plus Ky. So that will be, they also, these two Hamiltonian also are in a similarity transformation. So I have checked that for Kz equal to 0 plane, when Mx equal to minus sigma Z, and Mx inverse also minus sigma Z, and then I calculate this thing, and for this thing and that H minus Kx Ky 0, I am getting the same thing. So this Hamiltonian which I am talking about, this effective Hamiltonian, they are preserving this MX symmetry, and as MYT also written as minus sigma Z, this should also preserve this MYT symmetry. So this Hamiltonian and CZ can be written as a identity or sigma Z, sigma 0 matrix. So this Hamiltonian are preserving those symmetries which we are calling before. Now to see the dispersion from this effective Hamiltonian, when we put the value of A equal to 0, just do not taking this term, and when and putting those values of mx, my, mj, mx, my, kz equal to 0, so mz we do not need, then we will getting an equation of a ring which is just kx square plus ky square equal to m0 square, that will be 4. So that is the equation of ring for this particular Hamiltonian, the dispersion. And to make, as we know that, and in our ab initio calculation, we saw that these nodes are tilted. That is, they are not in these 2 points are not in same energy. So to make this tilt, we add an extra term in the Hamiltonian in the first term, C0, ky sigma 0, with preserving the symmetries. So with the value of C0, we can see that from this effective Hamiltonian also we are getting a nodal ring type of structure, and that is a tilted nodal ring. So from our effective model analysis, we can also show that for this as the symmetry are there for this Hamiltonian, they can also showing a nodal ring type of structure. And for while node also we have written a symmetry for this structure, for clockwise structure. With this symmetry CTZ, MXT and MY, we have written also a K dot P Hamiltonian. And as I already told that this MXT and MY is sigma z, and sigma z can be written in sigma z. So here also I have checked this Hamiltonian is preserving this symmetry or not. Then I check the things that my h kx ky 0 my inverse, that is giving the similar thing as h kx minus ky 0. So here also this my h kx ky kz my inverse is h kx minus ky kz, and mxt h kx ky kz mxt inverse is h kx minus ky minus kz. So this Hamiltonian also preserving this ETZ, MXT and MY symmetry. So for this Hamiltonian, when I am plotting the dispersion, I saw that there is 2 wild nodes. There is no nodal ring. For this Hamiltonian, we are getting 2 wild nodes. As in the case of ab initio calculation, we also see that for this particular structure, for those symmetry, we are getting 2 wild nodes. And here for this effective model also, we are getting the same thing. So, and I also write a effective Hamiltonian to control the direction of the nodal ring. So here in the Hamiltonian, those 2 terms come in the last. So with this Hamiltonian, we have not checked the symmetries for this yet. But with this Hamiltonian, we are plotting the energy dispersion. For the different values of C and D, we are getting the nodal ring in different direction. The energy dispersion for different C and D, we are getting nodal ring in different direction. That is shown in here. So from this effective model also, we can say that with controlling this value of C and D, we can rotate these wild nodes in different direction. So this is the conclusion. For anti-clockwise structure, we are getting a nodal ring as there are certain symmetry groups which are preserving the nodal ring structure around K point. And for clockwise structure, the nodal ring is breaking and we are getting 2 wild nodes. So by controlling the spin chirality of non-coordinate antiferromagnetic MCSN, we are getting topological tuning, which we also are getting by effective model calculation. We have also defined a model Hamiltonian for which we can control the nodal direction of wild node. And we have to finalize the result from first initial calculation. We have other results, so we have to finalize those things in future, and we have to check the symmetry analysis for the Hamiltonian, which is showing the control of the nodal direction connecting a pair of wild nodes. We have also planned to study non-trivial transport in other different type of non-coordinate antiferromagnets. And in my work, Dr. Ashish Nondi and Dr. Kartik Samanto and Pusta helped me a lot. So thanks to them. That's all. Thank you.
Okay. Yes, I may have missed. So in your model, by C and D, what you are changing?
Here I put this term CKY sigma x minus DKX sigma x. Okay. So for this term, if we change the value of C and D, we can get different direction wild node.
This is not a cross term, right? I mean, just show. No, so KY sigma x and that
K sigma x.
Sigma x is common.
Yes.
I see. You are differentiating between.
So one can write this is, I think, kind of a vector dot K and sigma x. So that vector term C and D you can write on a vector, and then ky kx, that is another vector, and then that will multiply with sigma x. And then actually that gives you a control on the rotation of the.
So Ashish, a general question. I mean, so as I understood, there are 2 parts to the work. One is, of course, the first part where you do the DFT calculation. The second part is this effective model. excuse me, how are you connecting the two? I mean, will you do this analysis of, let's say, the parameters here in terms of the materials?
So we are connecting in the sense that here we are not going to calculate. Eventually, one can calculate the parameters for CD or whatever there. But here we are not going to do that. But what we are going to, so the results are like that, that the topological transition, this from this is nodal ring to this transition is with the spin structure orient, the spin rotation is first time we have seen this.
Yeah. I mean, that's very nice. I'm just wondering. I mean,
and then we are seeing that people all do a K dot P Hamiltonian for materials thing. In order to see that whether the materials, whatever the symmetry in the materials, that is preserved in the known K dot P Hamiltonian.
I see.
And then whether I can derive that Hamiltonian, and that fit.
Derivation might be a long down process, but at least this the prefactors, if one can fix to some extent.
That prefactor one can fix. One can actually
From the DFT, that will be a nice thing because then there is some connection.
Yeah, so that is another point. Actually, this maybe he will do later also. One thing is that this while node, so people have shown this is the you're switching of this anomalous Hall conductivity. But here, if you change the chirality, actually you can go from a finite anomalous Hall conductivity to zero anomalous Hall conductivity.
Yeah.
So because the nodal ring, you will not show any Hall conductivity. So that means the switch on switch off mode you can actually achieve. So that's what we have seen.
Okay.
So
Okay. So I'm done. I mean, I don't have further questions.
And then actually C and D somehow connected to the phi of your experiment.
C and D connected with the
phi.
Here, yeah, you can say like that. That this C and D can be connected with your phi. Yeah. So this octapole. Yes.
Torque due to the.
Yes. But you have to find out that what is the connection. But for the time being, we'll work on the more details with the Hamiltonian. So let's see, and whose help to derive this Hamiltonian? Let's see.
Yeah, the two-band model is giving you the physics. Usually the while we start from 4-band.
4-band?
No. We do 4-band.
Okay. 4-band Hamiltonian. So the 4-band, actually, this is one interesting point since you asked that.
I'm not asking anything. I'm just.
No. Since you pointed these things 4-band, actually, I have some other question that I'll talk to you later. Okay. Even in this material, so I'll show you some results. Let's see that whether we can have some low energy effective Hamiltonian, 4-band Hamiltonian, basically. Okay. Any other question? Who's?
No, I don't have.
Yeah, I have one question both to Subhadip and Kush. Quickly ask, it's a very hard question. Can you go to the slide previous to the thank you slide? You understand what the question is, Ashish? You can guess. How old was Kush when this?
That's it. How old was pictures?
Kush, you have a quick comment on the question.
I don't remember even.
You look like this when you came for a job talk. I maybe remember.
But even this is
Whose
even,
one is very look like old, but mine was in 2020, 2019.
Yeah. You look a faculty. Kush looks like, just.
He was in Jalapur.
Yeah, graduate student.
Yeah. Okay, anyway, sorry for the sort of random
against
question.
250.
Yeah.
Okay, so thank you.
Yeah.
Yeah, thank you all of you. Yeah, good work. Keep it up.
Thank you, sir.
Yeah, Subhadip, you listen all this, whatever comments are there. Improve this thing. Let's see that.
Okay, sir.
Let's see that what I can do.
Okay, sir.
Okay.
Okay, sir.
Okay, then bye for everyone.
Okay, bye, sir.